All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203, section LO1. Hopefully you guys are doing well. Good to see you. Good morning. You guys some of you look way too energetic for this time in the morning, but that's fine. I'll be the non-morning person. Okay, let's jump into it. Boom. So, last time we didn't really do anything by way of the syllabus. We just sort of, we went through the syllabus, told you the rules of the class, things to expect. Before we start, I just want to do some announcements. So I've been having new students coming into my classes, so I figured it would be nice to actually put in the notes the class website. So that's it there at a glance. So that's what I put in the first announcement. Also, I did mention last time that there were 4 ways that I tried to contact you, from my Fordham email, from Jupyter, from Gradescope, and from Blackboard. And I wanted to make sure that everyone got communications from all 4 things. Pretty much everyone got from my Fordham email, from what I can remember, but not everyone got from the other 3. So you were supposed to check that you did or did not receive them, and then you were supposed to shoot me an email and tell me yes or no. Some of you I responded to, but not everyone. I just want you to know that the ones that I did not respond to, I'm not ignoring you. It's just that because I started getting a bunch of new students coming in, I just decided, you know what, I'll wait a couple days and then I'll just update everyone all together. I'll put in the new students and update the old students who weren't working. So if you did email me, just assume that I got it. And I would say definitely by Monday, if you don't hear from me, then it probably means I missed your email. But otherwise, just assume that I'm working on it, because I will be. So probably tomorrow, I'll update everyone and then send out some more test emails. And you guys should know, and I'll check on you guys on Monday. So if I did not respond to you, because I've been mostly focused on getting the new students signed up. So just be patient with that. If you did not email me, then you should, right? So I'm not going to really know whether or not it's working unless you guys tell me. So that's for the new people, as well as if you forgot to email me, then you should. Okay. Item 5. So those are the 3. Class website, you should expect 4 communications. If you emailed me and I didn't respond, don't worry about it. Until Monday, you should hear something from me. And if you did not email me, and or you're new and didn't get a message from everything, then you should email me, just so I know it's on my radar to check out. The 5th thing to talk about is just something that comes up occasionally, and it's definitely something that I found with my other classes this week. So I just wanted to be preemptive and nip this in the bud before we get started. And basically, it is a couple of my classes, they were just way too shy and way too quiet. And so I just wanted to make sure that everyone understands the implication of this. So that's what I did in item 5 here. I just typed a little thing up. So if you're a shy person and you're afraid of talking in class when I ask the question, it's fine. There's nothing wrong with it as a person. There's nothing morally wrong with it. However, you should understand that shyness can hurt you in some situations. It can put you at a disadvantage. There are times when you really need to speak up for yourself. You really need to let everyone know what you're thinking, what's affecting you, etc. And in the classroom is such a situation. The quieter you are, the less I will know to be able to help you, to address you, to make the class more useful to you. The students who are engaging with me will get the most benefit. And it is amazing how much benefit there is. They can literally not change anything else in their study habit, but have a conversation with me during class, and they will literally get better grades by doing nothing else different. It is amazing. And that's because your brain thinks in language. The more you can get something technical to meld with the language center of your brain, the better you get at it, right? So anytime you're not great at something, start talking about it with someone who's great at it all the time. You'll automatically get better at it. It's so crazy, but it's how your brain works. So don't be too shy. Try to say something. And what's more important, a lot of times we're afraid of being wrong, or we're afraid of not getting the right thing, or sometimes occasionally students are even afraid that, oh, if Jhevon's going to be disappointed in me, and he's going to think I'm stupid or something like that. None of that is true. I'm literally here to teach you. If you knew everything already, why are we here? You're wasting your time. I'm wasting my time, right? I don't expect you to know everything. I don't expect you to get the right answer all the time. In fact, I would say it's more important to talk if you don't know the answer and you're kind of sure, and that's the time you should talk to me, because that's when I would know, oh, there's this slight misunderstanding or this apprehension here. I should probably address that in class so that we're all better. So it's very important. So I just want to nip that in the bud. I'm not saying you guys are shy, but I just want to preemptively just kind of say that it's super important. Okay. It also, gets the feeling of, social engagement going, which is important for human beings. So don't be afraid to say anything. It's super duper important. And there are times when, so in either case, I mean, if you don't know the answer, or you're not sure, it's very important that you let me know, because I can correct it. And sometimes even if you feel like you got it, you should still say something, because there are times when you can be confident in the right answer, and it's not the right answer, right? So we actually had experienced that in the first class when I was doing that problem, f of x plus h minus f of x all over h, and I was doing things like sneakily canceling across sums, or not expanding the square correctly. And I was like, it looks good, right? And I'll see a lot of you go on camera like this, yeah, this looks good, yeah, that's awesome, right? And I didn't do that just to like mess with you guys and have fun with you and be like, gotcha, right? Okay, that's 1% of the reason. Hey, I've been teaching calculus for 15 years. I have to have fun too, right? But 99% of the reason was to show you that the mistakes I spoke about can sneak up on you when you're multitasking. If you're not really paying attention to them, it will sneak up on you. And then you'll end up in the situation where you feel like you're doing everything right, like you're understanding everything, but somehow you're doing bad on the test. And so you're like, oh, professor, I don't know what's going on. I understand when I'm in class, but I'm bad at tests, or maybe it's test anxiety. And you start blaming all these other things that it's not true. It's just you weren't paying attention to things you were supposed to pay attention to. And for you to know what those things are, one of the best way is to engage with me in conversation. And I can tell you, yeah, that's not the right answer, but this is why. You should be thinking about this, not that. And you have to be looking out for this, right? It's very important. Okay, that being said, let's actually just jump into the material of today. So the first topic in our syllabus is going to be exponentials and logarithms. Now, I'm not going to go as in depth with this stuff as I could, because technically it's stuff that I would expect you to know about. There's no calculus today. It's mostly like the algebraic stuff that you would have learned from algebra. However, students tend to not remember a lot about exponentials and their properties, and they really tend to not remember a lot with logarithms and their properties. So I'll spend a little bit more, I'll go into a little bit more detail with logarithms, but for the most part, this is just me doing a crash course. I just want to remind you of some important things that you need to pay attention to. And there's a smudge here. Okay, so that being said, shouldn't be a crazy class. So let's jump in. Let's hope my arm is awake. So let's start with exponentials. My screen is misbehaving. Okay, so hopefully you guys can see that. So just remind you of what that is. It's not really a definition. I don't know why I call it a definition. It's kind of not really a definition. But I just want you to see, I guess it's nicer for me to call the notation. I'm not actually going to define it. Okay. So it's like when you have something and you write a big thing at the bottom and then you write this little thing to the top right corner. That thing is called an exponent or power. Of x. So you can say it's x to the power a, x to the exponent a, all that good stuff. The big guy down at the bottom, that is called the base of the exponential. Okay, so that's what it is. And of course, we know the natural interpretation when a is a positive integer is this is multiplying x by itself a times. Okay, so I'm not going to go through that. Hopefully, you kind of knows that. Now, there are certain laws that you should know. So, for example, law 1, if I have two things of the same base and I multiply them, what happens? What's the result? That's when you guys chime in.
X to the AB.
Add
the exponents. A plus B, sorry.
A plus B, right? You add the exponents. What if I am dividing these guys?
You would subtract.
You subtract the exponents. What if I had something to an exponent? And by the way, your x cannot be 0 here. Remember, don't divide by 0. That was one of the things. What if I have something to a power and I raise it to another power?
You multiply the exponents.
Mm-hmm. So that's x to the AB. Okay. X to the 1. That's just x. That one's not so bad, right? 5. What is x to the 0?
1.
It's 1, right? And that requires that x is not equal to 0. 0 to the 0 is undefined for us. And there are going to be times when you see 0 to the 0, and we're going to talk about it as being indeterminate. So we'll talk about that in a little bit. But the basic reason is because if you see x to the 0, you can think of this as x to anything minus itself, right? A minus a is 0. Well, by the law above, that really means I took that thing and divided it by itself, which is why it gives me 1. And because of that division that's implicit, the thing can't be 0. 6, what else do I want to tell you about? What if I have a product of things and I raise it to a power? Turns out the power distributes. This also works for division. Of course, your y cannot be 0. And as I mentioned yesterday, note exponents do not distribute across sums. So if I had a plus in between the x or the y, or a minus in between the x and the y, and I had an exponent, it is not the same as taking the x and raising it to the a and taking the y and raising it to the a at the same time in general, right? If your a is the number 1, it's exactly the same. But for arbitrary values of a, that's not going to be true. So you need to remember that. What about x to the minus a? What is that?
1 over x to the a power.
Right. Of course, again, your x cannot be 0. And it's very important. This is a mistake that people make sometimes, so let me mention it. Note negative exponents do not affect the sign of the base. Very important. Sometimes students are tempted to put like a negative sign right here or something like that. Not true, not necessary. You cannot change the sign of the base by changing the sign of the exponent. If you make the exponent negative, it does a reciprocal. It does not make the number itself negative. So if I have 2 to the minus 1, it's not a negative number. It's still a positive number because the base is positive. It's 2, right? 2 to the minus 1 means a half, positive a half specifically. Okay. What about this one? Real fun one to just wrap it up. There's a fraction, x to the a divided by b.
Isn't this with like not like a square root, but
a radical, like
a radical, yeah.
Okay. How
Like,
do we?
Is it b that would be like outside of the radical, and then a? Like
it's the b radical or the b root of x to the a.
X to the a, yeah.
Right, and there are times when we can switch this up, right? Because I can think of taking the root first or the power first, and we can switch it up whenever our thing is positive. Which most of the time, pretty much all the time in this class, we're going to think of the base as being positive when we're raising to a power. And then that's because if your base is negative, you can get in trouble. For example, if b was 2, you get the square root of a negative number, and it's a complex number, and we're not going to deal with that. So for this guy, seems like you guys are less sure on this one. There's a mnemonic. And it's called flower power. So the idea is you have something to a fractional power. Basically, the idea is to think of that power like a flower. Right? The bottom is the root, which means it's the radical. So that's why the b went on the radical. The top is the flower, which, of course, rhymes with power. Right, so flower power. You know, the bottom number is the root. It's under the ground. The top is the power. Rhymes with flower. Okay, so that's how you'd remember. So like x to the 1/2 is radical x. X to the 3/2 is radical x cubed, etc. And one might be easier to calculate than the other. For example, a lot of the times taking the radical first and then raising it to the power is the easier thing. So if you had 9 to the 3/2, you don't want to cube the 9 and then take the square root of that huge number. It's better to square root the 9 to get 3 and then raise that to the cube and get 27. You'll know the answer is 27 without needing a calculator or anything like that. So those are just the rules. I want to make sure that you guys remember them. So what I want to talk about now is functions. So I want you to be aware that kind of like the quintessential form is, you know, y equals a to the x, where a is a constant. We assume it's a positive constant. Like I said, we don't want to worry about, it's not that it can't be negative, but there are many considerations that would happen with a negative base that I don't want to address in this class, because I'll have to teach you about complex numbers and complex analysis and all that stuff, and it just makes things too complicated. So I was going to think of the base as a positive number. Often, we'll consider a to be greater than 1 specifically. So a lot of the rules that I give you when I talk about the general graphs that I want you to memorize, we're going to assume a is greater than 1. And the reason is, if we understand what happens when the base is greater than 1, we actually understand all cases, because it turns out for any exponential function where the base is not greater than 1, you can actually rewrite that function to be 1 such that the base is larger than 1. And I'll show you an example of that pretty soon. X is your independent variable. Often called the input. So that's the value you control, and y is called the dependent variable. It responds to whatever value x you plug in. Depends on what x you plug in, often also called the output. So example, y equals 2 to the x is an exponential function. Y equals 1/2 to the x is an exponential function. I also want you to appreciate that this is the same as saying 2 to the minus x by the rules that we had above. I can distribute the x to the 1 and the 2, and then I would have 1 over 2 to the x, and then I can bring that up and make the power negative by the rules above. So notice in the first instance, the base is less than 1, but I can actually rewrite it as something where the base is greater than 1. And I'll always be able to do this. So there are times when we'll just pretend that the base is larger than 1 when we're developing general rules. So here, base positive less than 1 can be rewritten so that base is greater than 1. Okay, so rest assured, we'll always be able to do this. Non-example. Put everyone's favorite non-exponential x squared. Okay, so this guy is a polynomial, not an exponential. Right? Just because it has an exponent does not make it an exponential. Exponential means specifically the base is a constant and the power is a variable. If the base is a variable and the power is a constant, that's a whole different animal. They're not the same. They might look the same, or they might look similar, but notation is important, as I mentioned in the first class. It matters who is in what position. It matters a lot, a lot. Okay, so that's a very good non-example. What I also want you guys to know about are the graphs. So for the graphs, we will assume A is larger than 1. So I'm only going to graph the situation where A is larger than 1. Like I said, we can always rewrite things to be in this form, so we're good. If we understand how things work for 1, and it's not terribly important, but in the other class, I was putting rule lines to make sure I was writing straight. See? Yeah, I wasn't writing straight. I mean, it's not that bad, though. Okay, I'm actually very proud of myself. Normally, I'm like at an angle. Okay. You know what? Let's be brave. In this class, I'm gonna go. Yeah. All right. Okay. So the graphs. If I wanted to graph y equals a to the x, this looks like so. It is what we call asymptotic to the x-axis. It will always approach the x-axis from above. It will never actually get there. Tragic. Now, it will pass through 1. How do we know? Because we know raising to the 0 gives us the output 1. That was a rule. So when x hits 0, we're at a to the 0, which is going to give us a 1. Now I can do something like y equals a to the minus x. Some of you might remember what this does is it reflects in the y-axis. Not drawn to scale, obviously. That's also supposed to be 1. So that's what a to the x looks like when your a is larger than 1. If it's smaller than 1, it would look like the following. So 2 to the x would look like the guy on the left, while a half to the x would look like the guy on the right, right? That's because a half to the x, I can rewrite it as 2 to the minus x. Okay. So whenever the base is like a half, it's going to get smaller over time because you keep multiplying by a half. You keep having a half of what you had previously. Whereas if the base is 2, you keep having double of what you had previously. So that's going to increase. What if I wanted to write negative a to the x? Well, you might remember, and again, not the base is negative of the whole thing. You might remember that if you take the negative of a function, it actually reflects it in the x-axis. It kind of turns it upside down. So still passing through 1, negative 1 this time. And I could negate both. I could negate the whole thing and the power at the same time. However, that just turns the graph that I had up here upside down. Goes on forever. So negative 1. Okay. So those are all the graphs. In general, if someone just asks you, hey, what does an exponential look like? Most people would tend to think of the guy in the top left. However, you should understand transformations work, how transformations work, how if you make something negative or do something else, how it's going to affect the graph, how it's going to affect how the function behaves, all that good stuff. In light of above, recall linear transformations. Linear transformations, these are like geometric actions that we can take are linear. So things like shifting, reflecting, stretching, shrinking, shearing, things of that sort. And you can remember that when we do these things, there's a mathematical equivalent to them. So we can transform exponentials. So what I gave you was the quintessential form, the thing that you're really looking for to know you're looking at an exponential, but it can look somewhat different in the beginning, right? So you know you want the constant base and a power in the top. However, I could have started out like that and then multiply by another constant and then add another constant or something like that. And you should recognize it's still considered exponential. It's just a transformed exponential. So example, y equals 3 times 2 to the x minus 7 is an exponential function. If the 3 were a variable, like x times 2 to the 7, not an exponential function. For exponential functions, the base has to behave like a constant. Okay, but subtracting the 7 would shift the picture down by 7, multiplying by 3 would stretch it by a factor of 3, etc. But it's still going to have that overall behavior. Okay, so these are linear transformations. And of course, I can make the x negative. I could even add something to the x if I wanted to. It's still exponential. And that's because, you know, if I had x plus some number, what that really is a to the x times a to some number. And that's just another constant, right? I can just think of that as like a b. right? So if I add or subtract something from the x, it's kind of equivalent to multiplying it. So this is a very general form that can work. Okay, what else do I want to? I guess at this point I can talk about an important fact. Oh, that sentence was kind of lean. Look at that. Okay. Exponentials. Let me write it differently. Increasing. It would also work for decreasing. Exponentials change faster than polynomials. So i.e. they increase faster and decrease faster. So if an exponential and a polynomial they're both moving up, the exponential is going to move up faster in general. If they're both moving down, the exponential is going to move down faster in general. It might take a while to get this going, and that's going to lead into something that I'm going to talk about later. What's more important that you should know is that this is true for any polynomial. An exponential that's increasing will beat any increasing polynomial. And that's very important. So my base on my exponential can be very small, like 2 to the x, very small number. And I could have a polynomial with a huge power, x to the billion power. Eventually, 2 to the x is going to rise faster than x to the 1 billion power. It does not matter. X to the trillion power still doesn't matter. X to the trillion might win in the short term, but in the long term, 2 to the x will grow faster than x to the billion. An exponential is a different class of animal. They are not the same. An exponential grows faster than polynomials in general, eventually. It's very important that you know that. We can express this. So if I have an exponential, right, I can say it's going to be larger than any polynomial, and I put a double larger thing to emphasize that. And what that double larger thing means is as x goes to infinity, a to the x is larger with all caps than x to the a when a greater than 1. Okay. Yeah. And it doesn't, I can replace this a with some bigger number and it's not going to matter. Okay. So they're not the same tier. Let me emphasize that. Let's actually compare. Let's say we're going to compare 2 to the x versus everyone's favorite x to the a form, x squared. Okay, let's compare these two to really see what I'm talking about. And let's say I'm going to actually compare these pictorially. So let's say I'm going to graph the exponential in red and graph x squared in blue. Okay, what does x squared look like? What does it look like? blue curve.
Is it a parabola?
What does that look like? What's the parabola look like?
Like sort of like a U, where it's
Okay.
not really a U though. Like it goes
Yeah,
out.
yeah. And it goes through the origin, yeah. So like that, like that. Okay. Now on this picture, 2 to the x. Well, we already know what that looks like, right? It's going to look like this, right? It's going to pass through 1. Yeah. In fact, these guys are going to, just to give you a sense of scale, the intersection is at 2, right? So we're not looking very far out. This might be 8 all the way down here or whatever. But that's them, right? Now, this can be misleading. A lot of students will actually know these graphs and what they look like, and they'll be able to sketch it on paper, but they don't fully understand the implications. You see, if you look at the right side, when they're both increasing, the blue curve and the red curve, yeah, they're doing something different, but you might not think it's a big deal. Like, I mean, they're kind of behaving the same. You know, the blue curve is doing this, the red curve is doing that. One might be a little steeper than the other, but you know, they're kind of the same thing. This is not true. Not true in any. So this is the expectation. And I don't mean that in like it's not an official mathematical sense. I'm talking about like in the meme sense, MEME, expectation versus reality. We're going to do that. Right? So students will know these graphs. Like, yeah, I understand polynomials and exponentials. Yeah, you totally get it. Right? And they'll be able to sketch it for you. Right? And the thing is, they'll be like, on the right, they're not that different. You know, they're kind of both curving up. They both look like smiley faces kind of curving up. But what I want you to fully appreciate from this comment is that they are very, very different. And the thing is, it just takes time for you to realize this. So let me draw the picture again. Now, what we're doing is we're zooming out. We're on a large scale. So we're going off to like infinity, right? So this is like a bajillion, gazillion, like some huge made up number, right? Okay, so my 2 to the x, right, on this scale looks like this. Okay. Okay, what does x squared look like? So just imagine that some huge x. Still like a u, but it's like below it, right? What do you guys think?
Well, isn't it like steeper? So it doesn't go like as far out as it does with X?
So you mean like that?
Yeah.
But that would mean it's increasing faster, right? Steeper means you rise faster. So there's a point here where the x squared is larger than the exponential, which shouldn't happen. The blue curve should be under the red curve as time goes on. But how much under? Here's what it would look like at a huge scale. X squared might as well not even try. It's effectively 0. It shouldn't even, why did you wake up in the morning? Why did you think you could step to 2 to the x and like have a competition? In the short term, not much different. They're comparable. they're both smiley faces. They're both blah, blah, blah. When you zoom out is when you notice the difference. X squared is effectively 0 compared to 2 to the x for large x. It's like it's nothing. 2 to the x is so large that you can have x squared and the base could be a gajillion bajillion squared. But 2 raised to the gajillion bajillion power is so much larger than x squared. It's like you might as well be 0, dude. Like it's so much larger than you. You know what I mean? It's like compared to Bill Gates, I might as well have 0 money. Like, yeah, whatever my net worth is, like compared to him, like we're not on the same level. We cannot spend the same kind of money. Like we have different considerations. Like there's no comparison. Me and a homeless guy, if we compare ourselves to Bill Gates, we're pretty much in the same class of people, right? That's how I want you to realize what the implications are here. Polynomials and exponentials, not the same thing. X squared is effectively 0. It's not really 0. It's a huge number, believe me. But the 2 to the x is huger by a lot, by so much that if you zoom out, you won't even be able to see the x squared. It'll be like it's hugging the x-axis. So there are going to be times when we're thinking of large x's, and if we're comparing an exponential to a polynomial, I'm going to pretty much tell you, just imagine the polynomial is 0. And it's not because I'm like, it's not worth anything. It's because by comparison, it's like nothing. It's essentially 0, right? One person has $1, one person has $1 billion. The person who has $1 might as well have $0 when you're comparing to someone who has $1 billion, right? It's not, even if it's not actually 0, effectively it's 0 by comparison. And a lot of people don't really get this. And this is one of the things, I'll just take some time to go on a little rant here. This is one of the ways in which students in general just don't fully understand. I mean, for example, like we go through all these rules and we'd even remember the rules. We'll know how to do the manipulations. We'll know how to get the right answer, but we don't even know what those answers mean. And so what happens is we leave math class and then, we become these adults who are like, you know what? I've never used this math in my life. It's not important. And then you raise another generation of children who think that math isn't really important. It's just a thing I have to do. And it's because you don't realize the power. It's not just moving symbols around. It tells you certain implications. So what is an implication of this, for example? This knowledge would tell you, for example, that, you know what? Let's say you're a good saver. Saving your money under a mattress, bad idea, right? Let's say I take $100, save it under my mattress every day, right? My money's going to grow by $100 every month, let's say every month, right? Which grows like a straight line, right? And it might seem like I have a lot of money in the short term. Oh, wow, I made it to $2,000. Oh, I made it to $5,000. Oh, it's going to be really exciting for a while. But then someone else takes that same money, $100 a month, and they invest it in the stock market, for example, which after taxes is going to give them about 4% compounded interest per year. That means their money is growing exponentially. Now, in the short term, the first year, the first 5 years, there's not going to be much difference between you two. You guys are going to look very comparable. You're both putting away $100. You're making the same sacrifice. And you're like, that guy's going through this trouble of investing his money in the stock market. I just put it under my mattress and we're almost the same. So that guy's doing extra work. Yeah, good for him, right? What an idiot, right? And then it's like, when you both retire 30, 40, 50 years down the road, it's not comparable, right? $100 a month in the stock market versus $100 just saving in a checking account or under your mattress. One of you will be a millionaire and one of you won't, right? The guy who's investing $100 in the stock market, in 40 years, he's going to have about 2 million something. The other guy's going to have a couple 100,000. It's a big difference, right? And understanding what an exponential function is would be the thing that makes you know, hey, I shouldn't just save my money in a checking account. I need to get my money to gain compound interest, right? That decision, knowing that what the math says, allows you to make a better decision, right? And of course, you might be able to survive without doing this because you might just say, oh, I'll go find a financial advisor to advise me on how to invest my money. And that advisor would know about exponential functions and blah, blah, blah. But at the same day, you can kind of see if your advisor is like stealing from you or not telling you the right thing, you should be able to recognize, right? And the math is what helps you do that. It helps you make better decisions. And so it's not just about doing the calculations and getting the right answer and getting a check mark and getting an A and moving on with your life. It's what are the implications of this mathematics? What is it telling me about how I should live my life? It's very different. And this kind of explains a lot of things that a lot of people who don't understand math find mind-boggling, but people who do don't. So there are times when we'll see things like the ultra rich just keep getting ultra richer. You can have this billionaire who's like giving away millions of dollars, billions of dollars. And the next year, his net worth is even higher than it was the previous year. And you're like, how is this dude giving away millions of dollars and getting richer? The reason is his money is growing exponentially. And it's already a long way down the line. It's already at X equals a billion. So that person is up here. Whereas you with your money are down here. So you cannot understand how they can take certain actions and not ruin their life. This guy's like buying private jets. He's giving away millions of dollars. He's doing this, he's doing that. Yet he gets better over time. Man, if I splurge on a PS5, I'm in trouble for rent next month. And you're like, I don't understand how this guy can spend so much money and not be affected. And it's not that he's not affected. It's just that you're not noticing because you guys are on two different functions. You are imagining life as if you're on a polynomial, whereas that guy's living life on an exponential, right? And in a similar vein, there are times when you have ultra rich people who go broke, you know, wasted on drugs and money and women. You're like, how does this dude have hundreds of millions of dollars and then end up broke? And it's like, he was treating his money like a polynomial. He wasn't investing it correctly, right? That's how he could go broke. And so things like that is where you really start to see the difference. And you really start to see why the wealth gap is increasing the way it is. And I'm not saying there is no wealth gap. I'm not denying that. I'm not denying it's a problem. But a lot of the times when we think, oh, society's broken because these people seem to be getting ultra richer, and the problem is not society. The math, it cannot happen any other way because the math says so. And it's not that there's a problem in society that causes this gap to increase. It's just that where the money is going and how people are spending their money are very different. And so even though the level of the poor is rising, compared to how the level of the rich is rising, it's so different that you don't notice the difference, right? You kind of think that, oh, it's just, you know, society's unfair. No, it's not society. It's literally the math. Get the poor people on the exponential curve and you'll fix the problem. Teach them how to invest, teach them how to do things, teach them how to understand math, understand the implications, and make decisions based on it. Okay, I ranted way too long. Let's actually move on. But I do want you to get this implication. And there are other functions, by the way, to just blow your mind a little more if it's not blown already. There are other functions that compared to exponentials, they make the exponential seem like the polynomial. Like if you zoom out, the exponential is going to be the guy that looks like he might as well be zero, and so on and so forth. And it can stack and stack. So just want you to appreciate that. Exponentials and polynomials, not the same thing. And this has all sorts of implications. There are going to be rules that I'm going to give you guys for calculus where they're going to work in the exponent, and you treat it very differently if you have a polynomial versus an exponential. And this is why they're not the same thing. Okay. What else do I want to tell you? There's another important fact about exponentials I want to tell you. There is, in fact, an important example of an exponential function. So there's one exponential function that stands head and shoulders above the rest in calculus. Does anyone know what that is? Is it y equals 2 to the x, the guy who I've been talking up so far? What exponential function do you think is the most important exponential function? And I know you would feel like, they're all numbers. What's the difference? Like 2 to the x, 3 to the x, is one more important than the other, really? But no, there is an answer to this question. There is a most important exponential. This is the function e to the x. Now, like, wait, I thought the base had to be a constant. E is a constant. It's kind of like pi. Yes, I wrote down a letter, but that letter represents a number. This is e to the x. It's called the natural exponential because it's natural to use it in calculus. At least I think that's where the name comes from. I don't know. Don't quote me on that. This is the most important exponential function. E is a constant. Right, so it's I write it as a letter, but it really represents a number. So like pi, right? Everyone knows when I write pi, I really mean a number, 3.141598, etc. Right? So when I write down e, I also mean a number. E is roughly 2.71828. It's a non-repeating decimal. It's an irrational number. It's named after Euler. A lot of students call him Euler, but that's a mispronunciation. He's a Swiss mathematician. One of the most important mathematicians, actually. So we named a very prolific. So many things in mathematics textbooks are at all levels are due to this guy. It's not even funny. A lot of times when you're talking to math people, you're talking about, oh, use Euler's formula or Euler's rule or Euler's theorem. They're like, which one, right? You like it. There's so many. So essentially, this was the idea. So I told you how compound interest is crazy, right? Like if you're investing and your money's being compounded, it grows like an exponential. For instance, one reason why people get into credit card debt that is not just due to financial immaturity is that credit card debt grows exponentially, while a lot of people's money doesn't, right? And that's why in the beginning, oh, the minimum payment is just like $35. Oh, I just got charged $12 in interest this month. That's not so bad. Yeah, let's charge some more. And they don't realize what's actually happening. A credit card gets compounded every day. They add interest to your debt. And so if you don't understand what that means, you're going to think, oh, it's not a big deal that I just paid an extra $12. But you don't realize what's coming. In 5 years, if you keep that up, it's going to be a big deal. Okay, so now, credit cards, by the way, the typical credit card with the person with typical credit is going to charge you about 20% interest, 18% interest, compounded daily. If you have excellent credit, maybe you can get away with 12 or 15, but the average person is going to be 18 to 22 or something like that. Okay, and they compound every day. Here was a thought experiment. Question. Suppose you invest $1 in an account gaining compound interest of 100%. Okay, so they really are giving it to you 5 times more than a credit card would be. So pretend 100%, right? So we're adding 100% interest, but it's compounded continuously. And we'll actually go over this again at some point in the future. Continuously means we're adding interest an infinite number of times in a day, right? So it's not like we hit you with interest every day. No, every second, every part of a second, every half of a second, every quarter of a second, every Planck constant of a second, we're hitting you with interest. So we're continually giving you 100% interest. So now, what would be the balance after 1 year? Now, a lot of people think the answer is like, dude, an infinite amount of money. Come on. You just told us about exponentials. Those things are crazy. Now we're growing exponentially with 100% interest rate, and you're giving me interest on top of interest an infinite number of times. Dude, I'm going to be like a gazillionaire. Turns out the answer is E dollars. You'd have roughly $2.72, right? Euler figured that out. At least he's one of the first. And he could calculate this number to a very high precision. Like I said, it's a non-repeating decimal, so you can go forever and compute different digits and you'll never get to the full answer, okay? So that's where it comes from. And it just so turns out that this particular number is super important in calculus. And there are mathematicians out there, very respected, notable mathematicians, who actually believe the function e to the x is the most important function in all of mathematics, literally. It's definitely the most important function in calculus. And there are times when I won't derive every formula that I give you, but there are sometimes I'm going to derive some formulas, and you'll be surprised to know that most of the formulas from calculus, we derive them using this function. If we didn't know about this function e to the x, we wouldn't have formulas for a bunch of stuff. So it's definitely the most important function in calculus. Okay. So let's say I have an output. I have y equals a to the x, and I know the output value, and I want to find the input value. It turns out that I need a different kind of function to figure that out. How do you get to the input if you know the output, right? How do you kind of do the inverse, right? What is the inversion? That leads us to the other topic. Logarithms. So now let's actually talk about what a logarithm is. The logarithm of a number to a given base, so there's a base implied, is the power as an exponent. Logarithms are exponents. To which the base must be raised to give the number. Notation. How do we express this idea that I just wrote down? We write log. We write the base as a little number right here. And beside the log, we write the number that we're thinking about right here. And what we're saying, the logarithm to a given base of this number is equal to the power that I have to raise the base to get the number. This means if I take the base raised to the power that's on the other side, I will get the number that was beside the logarithm. Okay, so for example, if I write log to the base 2 of 4, what is that? It's 2. Why is it 2? Because if I take the base 2 raised to the power 2, I get the number 4. Okay? So that's what a logarithm is. Since or maybe I'll do a nicer example because not have all these twos. Let's do log to the base 2 of 8. That's 3. Why? Because if I take 2 to the power of 3, I would get 8. Okay, so that's what a logarithm is. So you'll realize that a logarithm is really just a different way to express an exponential equation. It's when I want to solve for the power. Notice that the 3 was up here in the top, and now it's down here beside the equal sign. So if that 3 were an x, I would know what the x was equal to. Right? So it's just another way to express an exponential equation. And you might wonder, well, what's the point of doing this? Why did you have to make math more complicated? I was fine with the expression 2 cubed equals 8. Why are we throwing this other thing? Why are math people always trying to confuse me? It turns out it's actually very useful. And kid you not, literally saved lives. This invention literally saved lives. It was invented by this guy called Napier for the purposes of making nautical navigation easier. Way back in the day, a lot of guys will go out to ship at sea and never return because navigating on the sea is not the same as navigating on land. It's easy to get lost because the distances are huge. Logarithms helped us to make the distances more manageable. So you'll realize in a lot of your science classes, you'll draw graphs in log scale for some reason. Like, why are we doing this in log scale? It's because the time period is so big that you can't really conceptualize the graph very well. So you actually compress the time scale using logarithms, right? So that's what a log graph is about. It gives you just gives us better analysis power. So now let's talk about the laws of logarithm. Okay, so I just invented this thing. Let's show you how it works. So law one is the definition, right? So putting the definition into mathematical symbols is the first thing you need to know how to do. Basically, this is saying if log to the base a of b equals c is the same as saying a raised to the c equals b. That's the definition. That's just something you should know, right? Log to the base 2 of 8 equals 3 is exactly the same as saying 2 raised to the 3 equals 8. It's just another way of saying it. You know, good morning, Ohio. Guten Morgen, right? They're all the same thing. They just have different expressions on paper. So that's what a logarithm is. That's the rule you should know. The left side is this expression means exactly the same thing as that expression. Okay. Now you might wonder, why do we need this other expression? Well, here I'm going to start to give you some properties that tells us why we like this expression. If I have a logarithm to some base of some number to a power, I'm allowed to bring that power down and multiply. In other words, a logarithm can turn an exponential thing into a multiplication thing. Multiplying is a lot easier than raising to an exponential, right? Because exponentials are a different beast compared to polynomials, right? So that's the case, right? So if I have, log to the base, if I have log to the base 2 of x cubed, this is the same time as 3 log to the base 2s. Here's another thing. If I have two things multiplying and I take the logarithm, it can turn into the log of the sum. Logarithms turn products into sums, right? Addition is a simpler operation than multiplication.
Wait, Professor?
Yeah?
For number 2, would that
be applicable if the n was on the outside of the parentheses? The x.
Very good question. I like that question a lot. That is very important. This and this would be considered the same. It is not equal, however, to if I put the n on the log, or I have the log in parentheses and the n is on the outside.
Okay.
Yeah. So the notation is actually important. Where the n shows up, yes, is actually important. And sometimes I might get sloppy and just write x to the n with no parentheses at all. And I'm talking about the first line. I'm talking about a guy like this. So this guy can be expressed in several ways. However, that means that the thing being logged is what has the power, right? But it's possible to put the power on the log itself, or log the entire expression, or put a power on the entire log expression. So that's actually a very good question. It is something that would come up later, but I'm glad that you guys are thinking on that wavelength to know how to actually write things down. It's super important, as I mentioned. If you take the log of a division, it's a subtraction of logs. By the way, I'd like to point out an analogy here. I want you to remember when we multiplied things of the same base, what did we do to the powers? We added them. When we divided things of the same base, what did we do to the powers? We subtracted them. If I took something to a power and raised it to another power, what did I do? I multiplied the powers, right? Remember, the log is the power. I was getting a phone call. And I just raised the power of x to the power of n. So multiplying the n by the original power is what we would do. So these rules, they are looking different, but they're actually a different way to express the previous exponential rules. 5. There's a very important formula called the change of base formula. And this basically says log to the base a of b is the same as log to the base c of b over log to the base c of a. Meaning I have a formula that can help me change the base of the logarithm. C is a convenient base. Of course, your a cannot be 1, or you would assume your a is greater than 1. I'll explain that later. Or no, not equal to 1. Okay. Now it's called the change of base formula because it allows us to change the base. Why would you need to change the base? Because sometimes the base we're working with is hard to work in. For example, if I were to ask you, what is log to the base 3? Or no, log to the base 4 of 8. Okay, so we know what this expression means. What power do I have to raise 4 to in order to get 8? Does anyone know? Well, let's think about it. 4 to the 1 power is 4. 4 to the second power is 16. We overshot the 8. So the answer is somewhere between 1 and 2.
Is it 4 to the 1/2?
4 to the 1/2 is 2.
Oh, never mind.
You mean 1 and 1/2? 3 over 2 is a guess? How do you know it's exactly in the middle? I mean, an exponential curve is like this. Maybe it's more to the left or more to the right. So if you're not sure, it's okay, because what you can do is change the base. If it's hard for you to think in base 4, you're not stuck to thinking in base 4. What would be a nicer base for these two numbers? What's a nicer base? Huh?
2.
2. Why? I easily know how to express 4 in base 2. I also easily know how to express 8 in base 2. So base 4 is kind of weird to think about. So what I can do is I can actually change this to base 2 by doing this formula, the change of base formula, right? So here I change it to base 2 because that's convenient. It's convenient based on the expressions that I have. And so now I can actually answer the question pretty easily. What's log to the base 2 of 8? Well, it's 3, because 2 raised to the 3 gives me 8. What's log to the base 2 of 4? Well, it's 2, because 2 raised to the 2 gives me 4. So the answer is 3 over 2, which you guys guessed. And you can check 4 to the 3 over 2. What is that? Well, we know that rule is the square root of 4 cubed. That's 2 cubed. That's 8. Voila. That was the answer. Okay. Now, remember, as I mentioned, E is a very important base to us. There are many times in calculus where we're given some other base, but we want to change it to base E. And this is the formula with which we're going to use to be able to do that. So the above rules must be memorized. The rules below are optional, but highly recommended that you just memorize them. Because your life will be easier. As well as you can probably test your study habits doing this, because if you're studying enough, you'll automatically remember these rules once you actually get through your studying for logarithms. So if you get finished studying and you don't automatically memorize these rules, it means that you're studying, you're missing something. So because they'll come up a lot, which is why I say you can figure them out based on the rules I already gave you, but it's just, they're so convenient to just know as quick facts because they come up a lot, which means that if you're studying enough, they should come up a lot. And if they come up a lot, you should remember them. So you'll probably automatically remember them. And if you don't, something's wrong with how you're studying. So here's rule 6. Log of 1. What is the log of 1? Well, it turns out that the log of 1 is 0. Why? Because a raised to 0 is 1. Just something to know, right? I could figure that out by knowing the definition of a logarithm, but it's just something I should know. If I see log of 1, doesn't matter what the base is, the answer is 0. What is log of 0? Now that's a good question. If I have a positive number, what power do I have to raise it to in order to get 0? Two to what power gives me 0? Well, let's look at what 2 to a power looks like. 2 to a power looks like this red graph. What makes that graph 0? Nothing. It never hits 0. It never touches the x-axis. If I raise 2 to the 0, I get 1. If I raise 2 to a positive number, it stays positive. It actually gets, it can get even bigger if my power is larger than 1. If I raise 2 to a negative power, it just puts 1 over 2 to the power. It stays positive. I can never get it to hit 0. Undefined. In fact, log of anything is undefined if it's negative or equal to 0. Because remember, we're always thinking of our base as being positive. There's no power you can raise a positive number to get 0, and there's no power you can raise a positive number to get a negative number. So this follows logically. Here's one that it sort of looks complicated, but it's actually very straightforward if you think about it. Log to the base a of a to the x is x. Why? Because I have to raise a to the x in order to get a to the x, right? Kind of just, but it's very nice thing to know. This one's a little bit more complicated to see why it's true, but if I put a log in the power of an exponential and the log has the same base as the base, that also gives me x. It's like the log and the base can cancel each other out. 10, and this one is somewhat of a notation. So it's not really a rule, but it's a notation I want you to be familiar with. If I write log to the base e, right? Remember, e is a very important base. We usually write that as ln, and this is called the natural log. Right? It's the log to the natural base. And it's a very important. So whenever I'm thinking base e, I'll write ln. In advanced mathematics, we don't change the notation, but for most science people, they would use ln to represent that. And we're already like 5 minutes over time, so I think I will wrap up there. What I'll probably do is maybe email you guys some problems to try, which again would make taking the test, the quiz on Sunday easier, in addition to going over the homework, going over the old quiz online. But for now, we'll stop there. Yeah. So thank you for your attention and participation. Hopefully that's okay. Any quick questions before we get out of here?
For the homework, you're referring to the textbook problems, right?
Hold on. No, I'm referring to the online homework at Cengage.
Okay, because I was having a bit of trouble with Cengage. I think I emailed you about it.
Okay, and it still wasn't fixed?
No, I was looking at having some problems with it.
Okay, maybe we should meet up later and talk about it then.
Okay.
I already have a scheduled office hour pretty much now, so maybe in another hour or so we'd be able to talk.
I can't then because I have class, but maybe you could email me some times that work for you.
Sure, we'll do that. That being said, have a good day, everyone, and I guess I'll see you guys in the next one. Ciao.